system is we can think of the mixture of the gas, liquid, or solid phases. So it can be 2, it can be 3, right? So 3 phases. So that's why we need to learn as a chemical engineer. You need to know the phase change operations. How do you change from one phase to another phase? Okay. So in terms of the chemical processes, for example, from solid phase to liquid phase, we call it leaching, right? Okay. So from the gas phase to the liquid phase, we call it scrubbing. And from liquid phase to gas phase, we call it distillation, right? And of course, you can transfer from liquid to liquid. So this is what we call liquid extraction. So this is the same phase, but you need to transfer from A to B. Okay? So from the liquid phase or gas phase transfer to solid phase, this is called adsorption. Okay? Of course, we give you some of the example in the industry, right? So this is PSA, pressure swing adsorption. And this is a industrial process of crystallization, which is from liquid phase transfer to the solid phase. Okay? So in the section 6.1, the important thing is that you need to know the phase equilibrium. And we use a kind of easy example to show you. This is what we call hypothetical experiment, right? So this is a phase diagram. We need to move from A point to B point, from B point to C, from C to D, from D to E. So we have a kind of process which can show you that, for example, in the point B, this is coexist of the 2 phases, which is the vapor phase and the liquid phase, right? Okay. So in chapter 6, we will always use this kind of use this as an example, and you need to use your imagination to think. Okay, because this is important. So I want you to know this kind of process well. So in the following lectures, it's easier for you to digest the lectures. Okay. So in the 6.1b, we started to know that how do you estimate the vapor pressures. The vapor pressure in the gas phase, of course, you can use the Bourdon gauge to measure the pressure, but because in the air or in a gas phase, the Bourdon gauge measure the total pressure, which is we call capital P. But if we have 2 species in the air, in the gas phase, I need to know the proportion of the pressure for A species and also proportion pressure for the B species. So how can you estimate the pressure for A species and also pressure for the B species? And this is what we call it vapor pressure, right? Okay, and then we start to know that what the definition of a volatility. Volatility is kind of degree, which how ease of the vaporization for a substance. Okay. So let's move to the most very important part of the section 6.1. This is called equilibrium equation or Clausius equilibrium equation. And I hope you still remember this is the end of lecture on Monday. I show you this equation. Remember? Sorry. Right. So again, I don't want you to remember this equation, but I want you to know the definition of these symbols, like P star. What is P star? Anybody want to tell me what is P star? Vapor pressure of a pure substance. For example, in the system, you have 3 types of substance, and each substance they have some partial pressure. So this is pressure here. So so you can see this is the pressure related to the temperature and the volume, and this is called latent heat. Remember, latent heat. V stands for vapor. So latent heat of the vapor is the transformation of the liquid phase to the solid gas phase. The energy required. So latent heat of the vaporization is the energy required to vaporize 1 mole of the liquid. So you don't need to remember this is 1 mole. Okay, so this is called latent heat. That's why as you can see, V over Kra is what we call specific molar volume, right? Specific molar volume. Okay, so let's start from this place. Is that imagine we have a system which is water in a container. So you have air in a gas phase. And so with the different temperature and pressure, you will have different water vapor. You have different water vapor. So if I change the temperature and pressure, you will have different water vapor. How can you get the answer of water vapor at a constant temperature or pressure? You can use this equation to realize P partial pressure of the vapor pressure of the water will be related to temperature, volume, and the latent heat. Okay? Right. So, and the first of all, the important thing is how do you determine the heat of the vaporization? How do you determine this one? Because P, T, and V is, we learn this, like in gas phase, PV equal to nRT, right? Okay, this is latent heat. So how do you determine latent heat? Okay, so if the pressure is not extremely high, so if this pressure is not very high, like 200 atm or something, this pressure is here. So as you can see, and the Vg over Kra minus this term will almost equal to this one, because will always equal to this one. Why? Because VL is very small, right? VL is very small. And this one, in this case, we follow the ideal equation of state. V over Kra G will be equal to RT divided by P star. Okay, so using these two terms, Vg divided minus VL is almost equal to G. So you can change the equation to become like this. Okay, so this is the condition 1. So condition 2 is that you have to change this. You have to remove this to make it become T and P. So in this case, V over Kra G will be equal to RT divided by P star. So you move the value to become temperature and pressure. So as you can see, you put this here and you get this one. Okay, and now this is a differential equation. So if you move the pressure to this part, and from right hand side to left hand side, you move the temperature from right hand side to the left hand side, you can get something like this. So this differential equation, as you can see, you learn this when you are in high school, right? This will become what? If you do this, you will get differential equation like this. The natural log P star divided by the reciprocal of T will be equal to this one. Okay? So this is under the condition of this one and this one, you can transfer, or you can make this equation, you can make this Krypton equation become this one. Okay? So, and now, do you know, so let's do it again. You can get something like this. So the good thing is, if you know this is differential equation, you can, if you use, if you have 2 points, you can get a straight line. As you can see, if the vertical axis is natural log p, and the x-axis, the horizontal axis is reciprocal t. So if you got 2 points, you can get a straight line, right? Because this is the, you can differential equation, you can regard this as a delta natural log p, right? Delta reciprocal t. Okay, so as long as you know 2 points, as long as you know the relationship between the partial pressure are the vapor pressure P and T, you can get a straight line. And as you know, R is a constant. So the slope will be what? Latent heat. So this is determination of the latent heat, or determination of the heat of the vaporization. Okay, so if the vapor pressure of a substance is measured at the several temperatures, you got several temperatures, okay, temperature will related to the pressure, and natural log P star is plot versus reciprocal T. The slope of the resulting curve is at a given temperature equal to this one. So of course you know this is a negative slope, right? Negative slope. So once you know the slope equal to a volume, value, and then you can get, because R is constant, you can get latent heat. Okay, this is the method most commonly used to determine heat of vaporization experimentally. So if you want to know the latent heat of the alcohol, or if you want to know the latent heat of the acetone, and this is the common way to find out using this equation, using Krypton equation. Okay. Next is called Clauser's Krypton equation. As you know, I just show you that if you Krypton equation, under these 2 conditions, you can get equation like this. Remember? Okay, so let's make it in another way. Because this differential equation, so if you find out this one, can you get another partial pressure? So let's change this again. Let's, under these 2 conditions, let's modify, or let's rearrange this equation to come like this. And at this time, because again this is a differential equation, so at this time you put the P in this on the left hand side, you put the T on the right hand side. So what you can get is this one. Okay, pressure on the left hand side, temperature on the right hand side. Okay, and again this is a differential equation. So if the heat of the vaporization of the substance is independent of the temperature, so if you do the integration of this equation from both sides, and R and latent heat is independent of T, so you can regard this as a constant, right? So if you do the integration in the both ends, you can get this equation, right? No problem. So natural log P star will equal to this one, because this is constant, right? So if you have this and you have a minus sign here, because this is the reciprocal T power 2, and plus B here, because B is a constant, because you do the integration. No problem, right? I'm sure you learned this when you are in high school, right? Or No problem, right? Okay, so what is this equation tell you? So now you have a constant. So if you find out the latent heat of the water, for example, using Clapeyron equation, right? If you get Clapeyron equation and you do it experimentally, and you can get latent heat. And now you need to know is constant B. Okay, constant B will be different in terms of varies from one substance to another. So if, for example, water will have different B, constant B. Alcohol will have different constant B, right? However, again, this Clausius Clapeyron equation tell you that what? Pressure is a function of temperature. I mean, vapor pressure is a function of temperature. Because this is constant, this is a constant, right? So you change the temperature, you will get different vapor pressure. Okay? So, again, so for Clausius Clapeyron equation, a plot of the natural log P star versus reciprocal T. This is a semi-log plot of P star versus T. Or this is semi-log plot, or you can use natural log P here, as you like. So in this case, you'll get a straight line, right? Because this is a straight line, you get this, and you got a slope. So slope is a minus sign delta h over k sub v divided by r. So you can get this. And the intercept is b, of course. But you can get latent heat. I just told you, you can get latent heat from the Clapeyron equation. This one. Okay? So, and you can get B from Clausius Clapeyron equation. So you complete this equation for any pure substance of the water, alcohol, acetone, whatever. MIBK, whatever. Okay? So, this is example 6.1-1 showing you that how do you get the latent heat of the benzene. And if I give you 2 points, if I give you temperature 1 and I give you the partial pressure or vapor pressure at P1, which is the benzene, and I give you temperature 2, and I also give you the vapor pressure of the benzene at temperature 2, which is here is that this is the information example 6.1-1 provided. So 280.8 Kelvin, and at this moment the benzene, the vapor pressure of benzene is 40 millimeter mercury. Okay, at a temperature 2, which is 288.6 Kelvin, and the vapor pressure of the benzene will be 60 millimeter mercury. So the question is the example 6.1-1 want you to find out the latent heat of the benzene and also the constant B. So he want the example want you to complete this one and this one to obtain this one and this one. Use these 2 points. And the question 2 is that if the temperature is 42.2 Celsius, and the question asks you what is the partial pressure of P3? What is the partial pressure or what is the vapor pressure of the benzene at temperature of 42.2 Celsius? So can you do this for me? Okay, so important thing is that you have these 2 points, right? If you have these 2 points, you can find out what? You can find out latent heat, right? So if you find out latent heat, you can put this number in this equation, Clausius Clapeyron equation. And then if you have and then you put this P1 into this in here, you can get B. You might say, perfect, sir, if I put the T2, P2, you got the same answer of B anyway. Okay? And then you put, and then once you get latent heat and B, you put a number, you put the T3 here, you can get P. Okay? So solution is that P star and delta P star and the delta T, you can get this. You can get this. You can from Clapeyron equation you can get delta. You can get latent heat. And then from Clausius Clapeyron equation you got B. And then from the, if you want to get temperature number 3 temperature, which is 42.2 Celsius, you use Clausius Clapeyron equation, got a P3 over P3 star. Okay, so this is the answer at page 38. I don't want to waste your time, so you go home and practice this by yourself. So very easy. You have 0.1, you got temperature and pressure. 0.2, you got temperature and pressure. I want to ask you 0.3. I give you a temperature, and I want you to find out the pressure. So if you plot your temperature at the x-axis, pressure at the y-axis, using the unit of the Celsius and millimeter mercury, you realize this is not a straight line. This is not a straight line. This is a curve. So you cannot. You have these 2 points. I want you to predict where is this point at temperature 43 or 42.2. So you need to find out what's the pressure using what? Using the Clausius Clapeyron equation. Okay? Right. So this is a very easy method to find out latent heat of the pure substance. Right. So, is any other way to find out vapor pressure of the substance? Yes. Here we introduce another method. The first one is called Koch's chart. Koch's chart. The Koch's chart and another one is Anthony equation. Anthony equation. So this is Koch's chart. So each line. So as you can see, x-axis and the y-axis. This is what? From 0 to 25, from 25 to 50, from 50 to 75 here. So this is not, as you can see, this is not a normal scale, right? So this is what? Log scale. We call log plot. And under log plot, you got a straight line for each substance. For example, this is water. This is ethylene. This is carbon dioxide. This is ethane. Okay? So if I ask you the temperature, if I tell you the temperature, you can get vapor pressure from the y-axis, vertical axis. Of course, this is American engineering system, right? This is Fahrenheit. This is a pound force per inch square, or square inch. So okay, let's take a look. Again, this is the vapor pressure is a function of temperature, right? So if I give you I give you a temperature here, and you can relate it to what? The vapor pressure. So, and this is a log plot, log plot, right? Log plot and log plot. Right, and let's take an example of water here. So this is a straight line of the water, right? This straight line of the water. So at this point, the point here is what? Is 374.3 Celsius, and this here is 374.3 Celsius, and the pressure is 218 atm. So what is this? TC and PC, right? This is critical condition. Remember? Critical condition of water. So there's no more. You cannot move this line upper. Okay? You cannot move the line upper. Okay, so this is called critical point or critical condition. Right, of course you got the N here. The Fahrenheit, 0 Celsius, 0 Celsius, and the vapor pressure is almost 0 because it's almost reached to the liquid, right? Okay. Right, and another case is mercury here. So if you have this Koch chart, it's easier for you to find out the vapor pressure. Right? So now you have learned is you find, if you still remember that when we use compressibility equation of state, in order to find out the compressibility factor, you can have a chart or a figures, and you find out compressibility factors according to temperature, pressure, or volume. And this is the one for you to find out the vapor pressure. Okay? Right. So next one is Anthony equation. And I want you to remember this equation because you are going to use this for your final exam. Okay, so you need to remember this. Again, the Anthony equation is the vapor pressure related to what? Temperature. So it's the function, vapor pressure is a function of temperature. And this equation is easier because, as you can see, P and T, and you have A, B, C. A, B, C are all constant. So it's a constant. So Anthony equation is a relatively simple empirical equation. Empirical equation means what? You do the experiment, and you get the number of A, B, C in order to accomplish this equation. Okay, so A, B, C will be changed according to different substance, or even different conditions of the temperature. Okay? So the data is extremely well. Okay. So P is vapor pressure, right? T is temperature, which we use Celsius. And P here is, you need to remember the unit, okay? Millimeter mercury. And ABC for several compounds are listed in the table B.4 in your textbook. Okay, so I'm going to show you this. This is the table B.4 here. So as you can see here, this is the Anthony equation. Okay, so you have different compounds, and this is the formula, and this is range, the temperature range, Celsius, and this is constant ABC. So this equation, you have ABC here, and it depends on different compound, different substance. You have different ABC, and even in the range of the different temperature. So I want to show you some of the example, the ABC here. I want to show you some of the example like water. Okay, the water here is that from 0 Celsius to 60 Celsius, the ABC will be these three, 8.1, 1750, and 235, which is ABC. But in the case of the water, the temperature range in is 60 to 150, ABC will be different, which is 7.9, 1668, and 228. Okay, so you need to know how to use this equation. T is Celsius, P is millimeter mercury. So in your final exam, please remember this. I shouldn't say remember because I will give you this equation. But you need to know what is ABC, right? Right. So here is a summary. Is for the single component phase equilibrium for P star. Tell me how can you get the P star vapor pressure? Clapeyron equation, right? You get latent heat. And, okay, I think I would better skip here because we are going to review this next week. Right, latent heat. I hope I hope you still remember the video I showed you. You know, when the temperature go up to 100 Celsius, when you keep on heating the water, the energy keep on giving this system to the water, but the temperature doesn't go up, right? So when the ice, you know, from the melting, is the same thing. From solid to liquid, the energy is about 333 kilojoules per kilogram at 0 Celsius. However, this energy can change from 0 to 80. So as you know, the latent heat, the energy is quite high, right? You keep this energy in the system without releasing it. But if you have only one phase, the temperature can go from 0 to 80 using the same energy. So any application for this kind of amazing heat, this is called phase change material. Phase change material. Imagine there's a material which can absorb the energy, absorb the heat, without releasing the heat out. And it can keep on absorb energy. And then when the temperature goes down, and it releases the energy release. Yeah, so this is one of the we call thermal buffer for hot days. Imagine you have a wall. You have a wall in the house, and you fill up this phase change material inside the wall. Right, inside the wall. If you take this out, there's a fill of a lot of bits. Okay? The bits absorb energy. For example, if the bit absorb energy, which the phase change material, which this transition is not 0 Celsius, is, let's say, 27 Celsius. Okay? So, if outside the temperature is 32, the energy will keep on giving this wall, right? So, this bit will absorb energy from outside, which is 32 Celsius. And the temperature will be here. Keep on, this temperature won't to change because the phase is changing from solid to liquid. And the temperature will keep on, will be at 27 Celsius. So the inside the house will always 27, right? Because the heat doesn't transfer from outside, which is 33 Celsius, for example, to the 27, because the wall stops the heat transfer from outside to inside due to the phase change material. And you don't need to have an air conditioner inside the house, right? So this is a kind of very nice material, okay? Environmental friendly material. You don't need to consume energy. But at night, if the temperature is getting cold, for example, the temperature is go down to 23, and this 27 Celsius will release the energy out. Okay, you will let the house become warm. So this is called phase change material. I have a video to show you here. What we call PCM. There are many applications because you use latent heat, so you can tune the temperature by different combination of the material inside of these bits. Okay, so it's amazing, right? No? Right. Okay. So so let's move to the 6.2, the Gibbs phase rule. Gibbs phase rule. So because chapter 6 we are talking about multi-phase system. So assume we have liquid and gas system in this case. And we want to duplicate the system. I mean, I want you to duplicate the concentration of this in the liquid phase and concentration of in the gas phase of the substance under some certain temperature and pressure. So when two phases are brought into a contact with each other, a redistribution of the components of each normally take place. Okay, blah, blah, blah. So you have two phases. So, for example, you have three species in the liquid phase. And these three, for example, alcohol, acetone, and water, they can vaporize, right? They will vaporize. And you want to know, under different temperature and pressure, remember I marked in yellow color here is that this can be changed or unknown of the temperature and pressure. But if you give a temperature or pressure here, you will get the different fraction of the ABC in liquid phase. You will also get different molar fraction of the ABC species. Okay? So as you can see, I mark all the red color in this place is that these are all unknown. So if I want you to duplicate the system, so you want to provide sufficient details for someone to duplicate it exactly the pressure, exactly the temperature, exactly the molar fraction. What you can do, you probably have to provide all the information, right? So he can duplicate the system. But as a matter of fact, you don't need to provide all the information. Why? Because liquid and solid has some kind of rules. If you follow the rules or equation, you don't need to provide all the information. Okay, this is what we call Gibbs phase rule. Okay, so the system can be temperature, pressure, masses of the phases, right? Masses of phases, value of the phases, density of the phases, more fraction of each phases. There are many informations you can think of. However, these variables are not all independent. So if you have some, for example, vapor pressure is related to the temperature of the substance. If you know the temperature, you can find out the vapor pressure. So I just give you the temperature. So I don't need to give you temperature and vapor pressure, two information. I just give you the temperature, you can find out the vapor pressure. Right? Okay? So do you provide sufficient information? Or how many information you need in order to complete or in order to duplicate the system? And remember this? This is the degree of freedom in chapter 4. Remember how many pieces of information required in order to get the answer. But before we talk about this, before we talk about degree of freedom analysis, there are two categories of the variables. One is called extensive variables, which is related to the size of the system. And intensive variables is not dependent on the size of the system. So normally, if we think of the condition, we always think of intensive variables, not extensive variables. For example, like a value or mass, we use specific value, right? We use specific density to represent the system, not the volume. Okay? So the intensity variables not dependent on the size of the system. So it can be pressure, temperature, and others, right? Density is specific values. Right. So, and also use the fraction. So now let's think of degree of freedom in Gibbs phase rule. So degree of freedom in Gibbs phase rule is how many pieces of information you needed in order to make the calculation in chapter 4, right? Degree of freedom. But in chapter 6 is how many numbers of the intensive variables that can be specified independently for a system at equilibrium. You learn the word of the equilibrium, right? If you reach the equilibrium, it's not the matter. There's nothing related to with the time, right? So the meaning of the term degree of freedom in the Gibbs phase rule is similar to its meaning in the degree of freedom analysis in chapter 4. Okay. However, the system need to reach equilibrium first before you talk about Gibbs phase rule. Okay? Right. So ladies and gentlemen, I want you to remember this 1, and you need to remember the Gibbs phase rule. If no reaction occurs among the system components, the phase rule is df stands for degree of freedom, equal to 2 plus c minus pi. What is c? What is pi? C is number of the chemical species. So in this system, how many chemical species in this system? For example, if you have water, alcohol, and acetone, you have three species. So C will be 3. Okay? And minus pi. Pi is the number of the phases in the system at equilibrium. Remember, it needs to be at equilibrium. So we call this pi. For example, if this system has a gas phase and liquid phase, so the pi will be 2, right? Pi will be 2. However, this is the equation which is not related to the reactions. If this system involves chemical reaction, then you need to use this one. Degree of freedom equal to 2 plus C minus pi minus R. R is the number of the equation, number of the reactions. Okay? Right, let's do some practice. Example, determine the degree of freedom for each of the following systems at equilibrium. First one, pure water, pure liquid water. How many? So degree of freedom, what's the number of degree of freedom here? If I say pure liquid water, so 2 here, right? And plus C, how many components here? Pure water, it must be water, right? And how many phases here? 1, right? Because liquid. So 2 plus 1 minus 1 equal to 2. So you have 1 component and 1 phase. That means the degree of freedom will be 2. That means what? That means you need 2 pieces of information in order to duplicate the system, or in order to complete the system. So what are these 2? 2 pieces of information, what are these 2? If you take a look at these phase diagrams, that will be temperature and pressure, right? If you give the temperature and pressure, you can address any points in this area because this is liquid. Right? So you need 2 pieces of information, which is temperature and pressure, for example, in this case. Right. Okay, another case is a mixture of liquid, solid, and vapor, water. So how many, what's the degree of freedom for the gas phase rule? So dF will be 2 plus C. C is how many pieces, how many components? Liquid, solid, water, vapor, water, right? So H2O, so only 1. Right? How many phases in this system? 3, right? Liquid, solid, and vapor, so 3. So 2 plus 1 minus 3, that means 0. So you don't need any pieces of information, and you can duplicate this system. So what is this? What is this point here? What's the point? What is the condition? What is the point in this phase diagram? Triple point, right? Triple point here, which is the coexistence of liquid, solid, and vapor. So you don't need temperature, and you don't need temperature. You don't need the pressure. You know, wow, Professor, the pressure will be 0.01 Celsius, and the pressure will be 0.00603 atm. So DOF is 0. No more information needed. Okay? Right. So triple point. Okay, so example 6.2-1 is Gibbs phase rule. I don't have time to talk about this. Before that, let's refresh ourselves first. Let me see that. Okay, I'm sorry. I think this is the last one. Let's complete this first. So example 6.2-1 is Gibbs phase law. So a vapor, this is another example, is a vapor liquid mixture of the acetone and the MEK. So you have a MEK and acetone mixed, and they both represent, they both exist in the liquid phase and gas phase. So acetone here and MEK here, and you also you have different temperature and pressure. So if you want to duplicate this system, which is, there are only two pieces, two components, right? So the molar fraction will be XB, and this will be XA. And XA will be 1 minus XB. So I mark here as an unknown. But here, if you know XB, you will know XA, because XA will be 1 minus XB. So no problem. So this is one unknown. And temperature and pressure is unknown at this moment. Okay? And, acetone and MEK also vaporize in the gas phase. So you also have a molar fraction of the MEK. Of course, you have molar fraction of the acetone in this system. Again, this is why this is marked in the red color, which is unknown. But YA will be known if you know the YB. So there are 4 unknown information. And I want you to duplicate this system. Can you do that for me? Yes, but before that, you need to do Gibbs phase rule first. You need to do degree of freedom first. So what is the degree of freedom analysis? 2 plus C. How many components? 2, right? Because acetone and MEK. How many phases? 2, right? Okay, so DOF will become 2. What does that mean? You have 4 unknowns. Among these 4 unknowns, as long as I give you 2 pieces of information, you can find out another 2. And that you can duplicate this system. I don't need to give you four numbers. I just give you 2. You can find out another 2. Then this is the meaning of the Gibbs phase rule. Okay? Right. So, for example, if I give you the temperature and pressure in this system, you can find out molar fraction of B and molar fraction in the gas phase, and molar fraction of B in the liquid phase. Okay? How? I'm going to tell you in section 6.3, because you will learn Law's law and Henry's law. You use Henry's law and Law's law to find out. Okay? So if I give you 2 pieces of information, you can get another 2. Okay, so let's play Kahoot now.